Hello, everybody, and welcome to the 7th Porous Media Tea Times talk. Sorry for the slight delay in starting, but today in the webinar series, we give early career researchers working on porous media a chance to present their research to the scientific community around the world. These webinars are meant to be complementary to the geoscience and geoenergy webinar series that you can find in our featured channels. My name is Arjen Massini from the University of Ghent, and I'm joined here today by Catherine Spirin from Imperial College, Maya Ruke from the Technical University of Eindhoven, and Kamalji Singh from Heriot-Watt University. If you like these webinars, please do not forget to subscribe to our channel to stay updated on our new videos. If you have any comments or questions for the presenters of today, please type them into the chat window to the right of the video, and we'll ask them at the end of each presentation. Our first speaker today is Tuan-tu Nguyen. He is currently finishing his PhD in electrochemical engineering at LRCS at the Université de Picardie Jules Verne in France. And his research focuses on the interplay between lithium-ion battery electrode microstructure and their performance. So with that, Tuan-tu, the floor is yours. You can start the presentation.
Thank you for having me on this Tea Time Talks. So I will present today a part of my PhD work, which focus on the study of the tortuosity factor of the lithium-ion battery porous electrodes. So my work is funded by the Grenot Group in collaboration with my lab at RCS in Amiens, France. So as you may already know, in every energy storage device, especially the lithium-ion batteries, in my case, for a porous structure is frequently used to make the electrode in order to promote a high specific interfacial area between different phases. So the active materials that you can see here on the SCM photos play a role as a host that accommodate the lithium ions. Inside the porous electrode, we can also find some additive other than just active materials like the carbon black as the conductive agent in order to improve the transport and the mechanical properties of the electrodes. This makes the porous electrode a very complex structure. So therefore, we often use macroscopic properties such as the porosity and the tortuosity to characterize this structure. While the porosity is clearly defined as it simply represents the volume fraction of the phase in the structure, the tortuosity is less straightforward to be defined and to be determined. The tortuosity factor of a porous structure is represented by the parameter called the tortuosity factor. The tortuosity of a porous structure is represented by the parameter called the tortuosity factor. So one way to define the tortuosity factor is based on the geometry of the structure. So it just it is equal to the square of the ratio between two distances. The shortest distance traveled by the spacey LP here, and the straight distance between the two points, so LCV. So, however, this symbol definition does not take into account the effect of non-uniform cross-sectional area of the pathway, which represent most of the real porous electrode. So that's why another common definition for the tortuosity factor, which possesses a more physical meaning, is shown here. So it represents the change of the transport property within the porous structure with respect to the intrinsic property of the birth materials. So from this definition, we can see that we can theoretically quantify the tortuosity factor by two different ways. So as we can either determine the effective ionic conductivity here, or the effective diffusion coefficient here. To do this, two electrochemical methods are widely used in this case. In the case of the porous electrode, the first method here present on the left is to use the diffusion-based approach, namely restricted diffusion method RDM. In simple words, the principle is to establish a concentration gradient across the porous electrode at steady state to create a diffusive flux here in yellow passing through the structure so that you can calculate the effective diffusion coefficient of this flux. Recently, a new method was developed, so-called cymatic cell method on the right. In this method, the ion come from the separator represented by the yellow arrow, meet the electron from the current collector, the green arrow, at the active material surface, so which reflect exactly the same process as when the battery operates, except that here in the experiment we use a blocking electrolyte, so there is no electrochemical reaction, but only the double layer formation. And using the impedance measurement, we can quantify the ionic resistance of the electrolyte within the porous structure, which can give us the effective ionic conductivity. So the key difference between the two methods is present here. On one hand, with the RDM method, we have a transport of charge through the porous structure. On the other hand, with the cymatic cell method, we measure the transport of charge to the solid and liquid interface within the porous structure, where the electrochemical reaction occurs. So the comparison of two methods has been done through experimental approach and show a good agreement. But the comparison using numerical approach didn't exist at that time, which could be interesting as it can give us better understanding about the mechanism. So that's why we decided to do this and to verify if the two methods give us the same tortuosity factor. And for this purpose, I got opportunity to collaborate with Dr. Sam Cooper from Imperial College London, who developed the Topwater application. So Topwater is an open source application for characterizing microstructure based on image data, including the tortuosity factor. So it is a powerful tool which can apply for all types of microstructure, and it's very easy to use. So if you are looking for a software to analyze your microstructure, you can consider it. So at the beginning, the tortuosity factor in Topwater was determined by simulating the diffusive flux through the porous structure as steady state. This simulation reflects exactly the statistic diffusion measurement. So we decide to implement a new module here in the Topwater application, which allowed users to determine the tortuosity with the same cymatic cell method presented earlier. So we also introduced a new term called electrode tortuosity factor, Tau-E, to denote the tortuosity factor determined by SCM and to distinguish from the regular tortuosity factor by the diffusion-based approach. And so now we can use Topwater for the comparison of the two methods. So here we use the conventional method for tortuosity determination on the simple 2D structure. Interestingly, as we can see here in the flux map, there are regions with very low flux or even no flux passing by that we are highlighted by different color here. So remove this region from the microstructure, give us the case B. So we repeat the simulation again, and we end up with identical value for the Mach-Mellin number. So if we remember that the Mach-Mellin number represents the chance of the transport property within the porous structure with respect to the burn property, this means that the effect of this porous microstructure on the effective property of the liquid phase passing through this the phase A and KB is the same, despite their different pore network morphology. So therefore, we decide to separate the pore network into two different types of pore, the dead end pore and the true pore, and study their effects separately. So this time with a different 2D microstructure made of sample pore network. In the case A, with only flux through pore, both methods show a good agreement for tortuosity and the Mach-Mellin number. And from the KE, we add the same amount of dead end pore to the main flux through pore, but with different morphology to give us B, C, and D. So for the KB, C, and D, with the conventional tortuosity factor, the RDM method, we obtain the exactly same Mach-Mellin number. So which means that there is no effect of the dead end pore on the transport through the microstructure. But with the SCM, we can see the different microstructure on the Mahmoudin number. So in our case, in the battery porous electrode, the SCM is more appropriate to represent the toxicity factor because the electrochemical reaction also occur on the solid liquid interface created by the dead end pore, which is missing if we use the RDM to measure the toxicity factor. So based on what we found so far, we want to emphasize the impact of the dead end pore in the 3D microstructure. So in order to showcase this concept, a 3D microstructure was generated having two adjacent layers with two different porosities. So within the 19% of the thickness, the porosity is set to 35%, but for the last 10% of its thickness, the porosity is set down to 20% as shown in the cyan box here. So the purpose of doing this is to close most of the pore in order to create long dead end pore which travel almost the entire thickness of the microstructure, thereby increasing the impact of the dead end pore. So in this scenario can also appear in view electrode, where the suboptimal manufacturing process can give a larger electrode density in the region close to the current breaker or the separator. So in this scenario, the toxicity value obtained from SCM is significantly lower than the value obtained by the RDM. This can be explained by the fact that the large fraction of dead end pore contribute positively to the transport to the solid liquid interface, but has no impact on the transport through the microstructure, where there are less available through pore, allowing the flow of species passing all the way through due to the high density layer at the end of the microstructure. Interestingly, when we flip up the microstructure and simulated it again with both methods, the diffusion-based method gives us exactly the same result because the true pore are the same from both sides, but for the SCM, the toxicity factor increased. So to summarize my talk, through this work, we demonstrate the key difference of concept between the two methods for toxicity factor determination, the RDM and the SCM, and we show that it needs to take into account the dead end pores, which are important in the case of porous electrode applied to energy storage application, and the cymatic cell method is able to capture the transport process in porous electrode better than the approach rely on the diffusion-based method. Thank you for your attention.
Thank you very much. Great presentation. The presentation is now open for questions. Please, if you have any, post them into the YouTube chat. We will read them out to the speaker, and then you can get a reply to your question. In the meantime, I would actually like to start with a question. So you showed us a new method for electrodes. Do you have ideas of how to measure tortuosity in other porous materials?
Okay.
Reactive transport also within narrow pores or dead end pores, as you've shown for electrodes.
So of course, so here you're right here. I'm showing to you the new method for toxicity determination of the porous electrode, because the problem with the battery porous electrode, that is the electronic is an electronic conductor, so we cannot apply the same method as for other porous media, which is electronic insulator. But for the other porous media, I think the RDM can work well, because if you don't have any electrochemical reaction happen at the interface, the RDM method can be appropriate for this porous media. But if you want to quantify the effect of the dead end pore, in this case, I think I put here. I think the one way to do is to measure the electronic conductivity, because for the other porous media, which is not electronic conductor, you can directly measure the electronic the effective ionic conductivity by just do the impedance measurement For example, here I present the method to measure the toxicity factor of the separator by just putting the separator between two lithium foil and measure the ionic conductivity. We cannot do it with our electrode because if you put the porous electrode in between the two lithium foil, we will measure nothing because the porous electrode is an electronic conductor.
Okay, thanks. May I ask whether you showed different dead end pores and how they affect the tortuosity? So do you have any suggestions of how to construct this structure of your electrodes based on what you found here?
Yeah, of course. Yeah, it's a very good question. Actually, from this reason, we can highlight the fact that, for example, in the porous electrode of the lithium battery, for example, we want to promote the high interfacial between solid and liquid phase, but we don't want to be penalized on the ionic transport. So, for example, if you can see the microstructure B, here I present the specific interfacial area. So you can see that we increase 4 times the interfacial area when we compare B and A, but the Marmolin number show us that the ionic transport is the effective ionic property is not be penalized too much because the Marmolin number of B and A is quite similar. So here, so the B for the porous electrode, I can say that the B is a good microstructure because it allows us to increase the 4 times the interfacial area, where we don't decrease too much the ionic properties from compared to the A.
It looks to me a bit like there would be a preference towards increasing roughness rather than nanopores into the porous material. Is this correct? So you would rather increase the roughness of the surface because this gives you a large surface area without penalizing the.
What I mean is, for example, if you need to consider between the B and D, you will better go with a lot of dead end pore, but short dead end pore, instead of long dead end pore like the case in the microstructure D. Because in the case of microstructure D, for example, here you can see that you also increase 4 times the interfacial area between solid and liquid. But then because the dead end pore is very long and very tortuous, so you end up with a very high Marmolin number. So for example, if you want to make some porous electrode with high power performance, you better go with the microstructure B. So here you can find a way to add a lot of dead end pore, but short instead of long dead end pore.
Okay, thank you very much. I do not see any questions from the audience. So are there any more questions here in the studio? Is there any? No? Then I would like to thank you again for the great presentation and like to move to our next speaker.
Thank you for having me.
Cynthia Michalkowski is a PhD student in a cooperation between Robert Bosch GmbH and the Institute of Modeling Hydraulic and Environmental Systems at University of Stuttgart. She is supervised by Professor Rainer Helmig and Dr. Veronika Schlepper. She started her PhD in 2018 and works in an associate project of the Collaborative Research Center SFB 1313.
Yeah, thank you very much. Thank you very much for the kind introduction. So I want to tell you something about modeling two-phase flow at the interface between the different components in a PEM fuel cell, and I use pore network modeling techniques for that. So first, I'd like to start to give you an overview on polymer electrolyte membrane fuel cells. So we have hydrogen and oxygen reacting to water, and that produces also electric energy and heat. So you have the reaction equations given here. On the anode side, we have the hydrogen supply, while on the cathode side, we have the air supply, and also the produced water has to be removed. In this talk, we focus on the interface between the GDL and the gas distributor on the cathode side, so that's also marked here. And dependent if we have two-phase flow at the interface, so if there's liquid water present at the interface, we have either an advective and diffusive vapor transfer, if that's not the case, or we have the formation of droplets and also the growing and the detachment of the droplets then. And then it also depends on the location of the breakthrough location. So where does the liquid water pass through the GDL? If it's in the open free channel where a droplet can form, or if it's nearby a hydrophilic wall where we have the interaction of different wetting properties and their influence on the flow. So the GDL is a hydrophobic material, while the gas distributor is hydrophilic. And the concept that I want to present to you captures the main influencing phenomena at this interface. But it's also simple enough to be combined with a pore network model. The reason why I use a pore network model, I will explain later. And another point is that it does not require the direct two-phase flow simulation in the channel. So I want to keep it simple and only have the gas phase in the channel to keep the model efficient. So these are the 3 points that I already explained. So we have the flow in the gas distributor channel. Here I use a 1D, one phase, so only the gas phase free flow formulation. And for the flow in the gas diffusion layer, so the GDL, I use a dynamic two-phase pore network model. At the interface in the channel, we have either the vapor transfer or the droplet formulation. And as I mentioned, if a droplet occurs nearby the channel wall, nearby the hydrophilic wall, we have the mixed wet interaction in the channel. And this interaction highly depends on the contact of liquid water with the hydrophilic wall. So I formulate saturation thresholds for this interaction. And the last occurring configuration is if liquid water passes through the GDL where there's no channel, so where there's this called land. And the liquid water cannot be removed from the GDL, but is in contact with the hydrophilic surface of the gas distributor. So we have a different capillary pressure saturation at this location. So it's a local different PCSV curve is applied there. So let's come to the pore network model. So you see the GDL structure. It's a fiber structure, it's a hydrophobic material, and it's quite heterogeneous. This is only a small sample where we have 1 millimeter in each size, and the thickness of the sample is 165 micrometer. And you see that there are different pores of different sizes, and we are interested in pore-scale effects. So we really want to consider the processes on the pore scale of the porous material. So a well-established technique here is using a pore network model because it's quite efficient, but still on the quasi-pore scale. So I use pore-scale to generate a pore network in this structure. So it really represents the initial structure, the initial fiber structure of the porous material. For those who are not familiar with pore network modeling, you can compare it to something like an electrical network. So you have a network of pore bodies and throats connecting them. And for the throats, you can use something like a resistor. And for the pores, you would have a resistor-capacitor combination. And considering that in the fluid dynamics means that we have pore bodies which have the volume of the void space of the porous material, and we have the throats who are related to the resistance of the flow. We also assume low Reynolds numbers in the throats. That is important for our flow formulation. And as I mentioned, we consider two-phase flow. And we consider the invasion of the non-wetting fluid in the network. So we have water in a hydrophobic network. So it's a drainage process. And the accessibility, meaning if a pore can be invaded by the liquid phase, depends on the threshold pressure. So a certain threshold pressure needs to be overcome in a pore such that the liquid phase can invade the next throat. Also, since we have a fiber structure, our pores have some edges and some corners. As a simplification, I use cubic pore bodies, but that allows us to consider the wetting film. So the wetting phase is always connected in the network, and there are always corner flows and film flows through the throats and the pores. considering the equation in the pore network, we have a volume balance formulated for each pore, for each phase. So the saturation change in time in each pore depends on the fluxes in and out of the pore. The fluxes are calculated using Washburn formulation. So we have the conductivities of the throats and the difference of the phase pressures between the two connected pores, which gives us then the flux. Since we do not only consider the phases, but also the components in the phases, we also have the transport equation with the advective and diffusive fluxes given in this set of equations. So these are the equations that solve our flow through the hydrophobic pore network. However, there are still some closing equations missing, and that's the key point of such a pore network model. So how to formulate the local rules. So for example, the local capillary pressure saturation relation. Here we have a formulation derived analytically from Vahid Niaza in 2010. And it's formulated for cubic pores and depends on the surface tension, the contact angle, and also the size of the pores. So this is a local formulation, how the fluids behave in the pores. And we want to use these formulations for our interface configurations. So we have here the complex interface of this fiber structure in the channel, and we want to simplify that to local rules. So we distinguish between the three scenarios. So we have a droplet in an open channel. We have the interaction of the hydrophilic surface below a land, so where there's no contact to a channel and the liquid water is not removed from the network. And we have this intermediate state where the liquid water is in contact with the hydrophilic surface but can leave the network, so can leave our GDL. We start with the last configuration. And as I mentioned, for the contact and the interaction with the hydrophilic wall, it is important to define when does the interaction start. So when is there an influence of the hydrophilic wall on our liquid water? And therefore, I define a saturation threshold. So I say that there needs to be a certain amount of liquid water present in the boundary pore such that the interactions start. And this saturation threshold is defined analytically based on the geometry of our pore. So for a cubic pore, for example, we see that our liquid phase needs to form a complete sphere before we have to contact. And that's how we formulate the starting criterion. So this starting criterion here is formulated especially for the cubic pores. For the stopping criterion, so we have now the criteria fulfilled and the interaction between the hydrophilic and the hydrophobic part of the pore starts, but it will also stop since through the hydrophilic throat, a lot of fluid might flow out, and at a certain point, a snap-off occurs in the pore body. So we also need to define something like a threshold for the stopping. But as you see, that's a little more difficult because it highly depends on the configuration of the pore. So which throats are connected, which throats are invaded. However, I'm currently working on a paper on that where I explain in detail how to find this stopping criterion and what influences these criteria have. So I would refer to that for more details. Now we come to the second configuration where we have the blockage of a hydrophilic wall. So the pores now have something like one hydrophilic side and the rest of the pore is hydrophobic. And again, we have a certain threshold when this influence of the hydrophilic wall starts. Since the throat, so if the pore is not invaded at all, it does not make any difference if it's hydrophilic or hydrophobic, if it only one phase is present. Then when it's invaded for the first time, at a certain threshold, the interaction starts, and that's when the hydrophilicity comes into play. So until the threshold, we have the general formulation for the capillary pressure saturation relation for a hydrophobic pore or for a hydrophobic cubic pore. But after the threshold, the curve changes a bit. So here you see in orange the new formulation, and the dashed line is the old hydrophobic relation. It looks a little complicated, but it's also derived analytically, and it's similar to the derivation of the general hydrophobic formulation. And yeah, it's just the geometry that makes it look a little complicated, but the derivation is straightforward. Now we come to the last part, and the last part is a little tricky because droplet occurrence and formation is it's a difficult topic in porous media, and I try to use to formulate a criterion by attaching another interface pore where the droplet can form. So there is another pore which represents the channel or the free flow where the droplet is forming. And then I can again apply local rules, so like a capillary pressure saturation relation, defining the behavior and describing the behavior of the droplet. And in this case, we have the formation. So there is the throat, which defines the contact area, and a drop is forming until it reaches the critical contact angle, so the contact angle of the hydrophobic surface. And then at a certain size, when we have reached our critical contact angle, then the droplet size, so that the contact angle does not change anymore, but the contact area changes. And that results then in this curve that is plotted here. So the blue part represents the part where the constant contact area and the contact angle is changing, and the orange part shows the curve which results from a constant contact angle and a growing contact area. For the detachment of the droplet, then we have a force balance, and that depends on the gas flow that we have implemented. So there are also external forces acting on this pore, but that's independent of our local rules or our local capillary pressure saturation relation. And with that, I want to thank you for your attention. Here's another overview on the different configurations that occur at the interface. So we have the blocked pores, we have the mixed wet interaction, and the interaction in the channel where we have vapor transfer and the droplet formation. And if there are any questions, feel free to ask. Thank you.
Thank you, Cynthia, for this fantastic presentation. I've learned a few nice things from the cartoons or schematics there. To our audience, please, if you have any questions, please type in the chat box on your right-hand side. I've got in the meantime, I've got two quick questions, probably naive questions. With the GDL, you have certain thickness there, and you put a pore network on inside this GDL. Mm-hmm. Thickness, does it affect your two-phase flow? Let's say the movement of droplets, in which direction is going to go. Is there any optimized thickness we can have, or because I'm not familiar with the area there, to be honest. I'm just asking that if the thickness can affect the flow of things there.
Well, yeah, that's a very good question. The properties, so especially the geometric properties of the GDL, have a high influence on the flow behavior inside the GDL. So on the interface, it mainly results in different breakthrough locations. So if the paths for the liquid water, how to pass through the GDL vary, then we also have different interface configurations. And the thickness itself then mainly has an influence on the flow through the pore network. Considering the application of a fuel cell, there are different criteria to take into account. So how to choose the right material. So for example, the GDL also has an influence on the stiffness of the cell. So you also need to have the mechanical stability, and there the thickness has a high influence. On the interface itself, so if we really want to focus on the influence on the interface, I think the main influence could be that if the GDL is too thin, then you might only have like 2 pores in a row for the path of the liquid water to pass through. And then, for example, a droplet detachment or the mixed wet interaction would have a high influence on the flow behavior. So like the whole path might just collapse and another path might form. So it's not that you only just rip off the last path of the breakthrough, but the whole path might just break down and another path might form. That could be an influence if the GDL is very, very thin, so if you only have a few layers of pores. But I think in the other direction, so if the GDL gets thicker and thicker, there is no no effect on the interface that you would just observe.
In your simulation, how many pores do you have in that thickness? What's the average number of pores you have?
So in that quite small sample, so 1 millimeter by 1 millimeter is not really sufficient to show the whole properties of the GDL, but it was sufficient for this example to show the different interface configurations. So in this 1 millimeter sample, I consider 2,000 pores, but many of them are very small. So they are too small such that there's no liquid water invasion. The pores that really define the interaction are only a few. So only the largest pores are invaded by the liquid water. So if one is only interested in the liquid water pass through, one could reduce the network size to just the largest pores and neglect the smallest one. So the smallest pores are more important than for the gas transfer, since the large pores are then blocked by the liquid water. So it always depends on the application that you have. But in the setup that I showed here, it was approximately 2,000 pores.
Okay, thank you, Cynthia, for these explanations.
Thank you for the question.
So we got thank you. We got a couple of questions from the audience. The first one is from Farhad Irazi. He asked, what algorithm did you use to extract the pore network of your structure? What's the shape of your pores, spheres or cube in that?
Okay, so the algorithm I used is a watershed algorithm. So it's based on the pore-scale code. And it extracts something like regions. So independent of the pore shape, it just tries to find the largest void spaces, defines them as pores, and the connections between them. So the narrowest point is then the throat connecting the different pores. So in the segmentation algorithm, the pore shape does not really play a role. I just have the volume of the regions. And this volume I then adapt for the cubic pores. So the pores it's a simplification to use this simplified structure and simplified geometries. But as I mentioned, it shows the main influencing, like having the corner flow that is included then. But for the segmentation itself, the pore shape does not play a role. This is only the volume of the void spaces.
Okay, thank you, Cynthia. We got a question from our own Catherine. She's asking on your slide number 17, where you plot PC, versus saturation. The PC changes is more extreme when the contact area is changing. With the orange line compared to the contact angle. Would you say the change in contact area is more important in the dynamics?
Well, that highly depends on the curvature. So the capillary pressure is directly related to the curvature of our surface. And if we have a small throat, then the curvature changes a lot while we keep the contact area constant. And changes less when we keep the contact angle constant and the contact area changes. So yes, the contact angle has a high influence on the PCSW curve for the droplets. If it's more important in the dynamics, that's difficult to say, because the contact angle hysteresis is not considered here. That's only considered in the force balance that I didn't show in this talk. So yeah, I hope I answered the question.
I think that's clear. Yeah.
Important.
Yeah. Thank you, Cynthia. We got another question from Yusuf. He's asking about the computational capacity needed to carry out these computations. For example, is it possible to model a complete GDL layer or several layers? I think you've touched upon that, answering my question. But I think if you want to add some more, please go ahead.
Well, it is not possible to model a whole GDL. So as I mentioned, it's just 1 by 1 millimeter, and in a fuel cell, you would have a GDL of a size like 10 centimeters to 30 centimeters. So it's about, it's huge compared to the small sample that I considered. With the pore network model, you are able to consider a representative volume element, which would be about a centimeter by a centimeter. That's then you are on the safe side to really capture the REV properties of the GDL, and that is doable with the pore network. It takes some time, but on a cluster with good performance, that's good. But yeah, it's not possible to really model the whole GDL layer with the pore network model. There you need to use some REV properties, and you could, for example, take the findings from the pore-scale and try to improve the REV model with them. But that's another story. So
Thank you, Cynthia. Any question from from our organizers here in our studio?
Yes, I got maybe one more question. Thank you very much for your interesting presentation. I was just wondering, have you also done maybe some micro model experiments where you looked at how these fluid configurations inside a pore develop, especially in the mixed wet case?
Yeah, so I started with some experiments using PDMS models to investigate the influence of different wetting properties of the material. However, due to Corona, the lab had to be closed, so I'm not done with the experiments yet. But the colleagues continue with it, and yeah, I'm looking forward to get some results. So it's a good point. There is some validation necessary. So we started with the experiments, but they're not done yet.
Okay, thank you.
Thank you, Cynthia. I had the same question, so I'm glad that I didn't ask because I forgot about that. Yeah, thank you. Any other questions? If not, I don't see any other questions in the chat room. I'd like to thank you, Cynthia, once again for joining us and accepting our invitation. It was a pleasure to have you in our studio. Thank you.
Thank you for the invitation.
Okay, so with this, I would like to close today's session. I hope you have enjoyed the session. If you have any comments, please do write us an email on this porousmediattt@gmail.com. With this, I would like to take your leave, and then we'll see you in 2 weeks. Thank you once again for joining us today. Take care. Bye.